Wrestling?
Cool. I'm streaming for the tennis players. So no profanity today. I have 0 people watching right now.
Yeah, no profanity in general.
What window? I didn't open anything. What happened? I don't know. I didn't do it. Shut them if you want to. Yeah. No, I'm trying to quit things. I have that.
You're doing yourself?
Oh, you're having them do the still wool?
Yeah. Just regular. I'm streaming this right now.
How is it any of this right there? Like live stream?
Yeah, but you can't be on there because you're a minor.
Oh, yeah. Wait, why is not going to be here?
Henry. Actually, it's just Henry and Alex. I'm streaming this. Oh, problem. Bunch of good students. Yeah. I know I didn't post it. It's I got several emails.
I'd rather get Chris about and go to this line.
I have one person watching. I don't know. It doesn't say.
I thought you can check.
Well, I don't know. How do I click? Oh, they just went off. Okay. Never mind.
What channel is this?
It's my school one. Matt Markarian at Madera USD. Yeah, you can go on your favorite Chromebook. It should. I'm wondering if it'll let. It should, right? Yeah, it's at Matt Markarian 8820.
Hey, Dylan's not gonna be here. I think he has a tournament.
Oh, you can watch this too.
He's live streaming already.
I'm live streaming.
Wait. She watching his live stream.
So I got to deal with like 4 different screens because I got the notes on the live stream.
Is it on Twitch or?
Yeah, it's on YouTube live.
Oh.
Because because I can use my school district email and YouTube channel. I can't have you guys on camera because you're minors. Yeah. I know. I don't know how this. If anybody can check the sound, let me know. But
What's the Instagram?
it's at Matt Markarian 8820. Apparently, I'm.
Wait, can you hear it?
Is it okay? The sound?
Oh yeah, you can.
Oh, good. Okay.
You're just in the door. Yeah. The next one, can you talk to him?
Why don't we just do it?
Cal? He's online.
When I bring you guys in the room next door, and I'll teach you.
Topic's so important thing is to.
Well, it is buffers, which is it can be tough. So I just don't want the echo. So thank you for testing it. Now mute it. Yeah. I'm so nervous. I'm not used to being on.
Potentially helpful.
It's not. Yeah.
Now my experience on YouTube.
What? Oh no! Now everybody's gonna do it, and we're gonna lose focus on the action. I shouldn't have said it again, but then people.
Look, yeah, I did.
All right, so we're gonna skip the warm up today, just because I want to make sure we have enough time for this today and Monday. Buffers are often a topic that are a little. It's kind of tough to wrap your mind around it initially, but it's really nothing different than we've already been doing. The application just seems kind of tough at first. So we'll get into that. So again, it's a difficult concept, like it says over there at first. Okay, can you please? I asked you guys not to have the volume. Okay, and I disabled comments, so people can't comment. Yeah. Okay. No, you can. Oh, I had it turned off. Yeah. Okay, we do need to focus on this though, and not the live stream, or I'll just shut it down and Henry will be cooked. So yeah, they can be a difficult concept at first. So it'll really help to pay attention today, and I'm glad you guys are here that are here. So I'm going to put them up on the other screen too, so both they can see it from another source when they go to watch it. I have 3 people watching, and they're all in this very room. Okay. So we have a definition there. Okay. Buffered solutions resist changes in pH. That's all they're there for. A buffer, like when I think buffer, I think of me going away to college. I wanted to go somewhere. I didn't want to go to Fresno State, which though that probably would have been a good idea looking back, because that's where I ended up getting my credential anyway. But I wanted to go somewhere far enough away where I had a buffer between me and my parents. And they don't watch this channel, so they don't. But they already do. Yeah. And my younger son's going to probably do the same if he goes away to school this next year. So it's healthy, I think, to have that buffer. So it basically resisted them like just making a drop-in appearance at the dorms, because that was 600 miles away, 10-hour drive. And likewise, I couldn't just run home, and I didn't have that safety net of just being able to go home and get laundry done and stuff. So when I say buffer for family, like sometimes it's good, sometimes you need that. It kind of resists them just making those sneak attack visits where you didn't know they were going to show up. Okay. In a buffered solution, it's kind of the same idea in that if I have a buffered solution, I start adding a strong acid or base to it, it will resist changing pH more than a solution that's not buffered. Okay. And so we're going to look at how that is. It's a common ion issue, honestly. It's really what ends up happening. Buffered solutions are common ion problems. The buffer problems are usually common ion problems. So if I put something that's a common ion in that solution and I go add something strong to it, because we're talking weak acids and bases. If I have a weak acid buffered solution and I add a strong base to it, it's going to resist the change in pH to rise real sharply. Okay. And so it can be overcome. This happens in the ocean. We like barely mention buffers sophomore year of high school chemistry in ocean acidification, and we say buffers are just substances in the ocean that keep the pH where it needs to be. And if you get too much acid, it can overcome the buffering capacity. The pH of the ocean drops. Shellfish start dying because their shells get dissolved by the acid. And so, but we don't really go into like how it works chemically. And so, because it's pretty high level stuff. Okay. So here we've got two equations. We have a weak acid. That's the base. This is what?
Conjugate base.
Conjugate base. Yeah. Why is it a base? Yeah, the leftovers from the acid make the conjugate base. Okay. Leftovers from the acid make the conjugate base. And then it makes water on the base and because the H from this gets together with the OH and makes H2O. Okay. And what's left is the conjugate base. Okay. So buffered solutions can contain a weak acid and its conjugate base, or a weak base and its conjugate acid. Okay. And again, also in that solution, you've got the acid going back and forth in equilibrium. They're both, this is all happening in one container. So it can get, kind of confusing at times, but once you start seeing the problems, I think it really helps. Okay. So there's steps for buffer problems that you want to follow. And I put these in the notes just so you can use it, and you're going to see this as we go through it. The first step is to do a dilution if needed, and you'll know by looking at the question if you have to do that step or not. Our dilution equation is M1V1 equals M2V2. We've used it before in here. We used it in a couple of labs, the Blue Dye lab, stuff like that. Okay. Then step 2 says do the stoichiometry, and it says you can either use an ice table or dimensional analysis. I prefer the ice table because it's easier to deal with than setting up a string of dimensional analysis problems. Okay. Then it says, and by the way, the ice table and the stoichiometry part, we actually call it something else. We call it a BSA table, but we'll get into that. Okay. Then we do the equilibrium calculations if a weak acid or base is involved, which they will be in this. Okay. So we'll talk about what those are. You've been doing those calculations already, like what we've done in the warm-ups and in the notes. We're just adding a couple of steps to it. Okay. Yeah, because what we're doing, why we have the solution is so it can resist the pH changes when we start. Like when you guys do titrations in labs, there is that point for those of you guys that did one in my class where you're trying to get it light pink and it's clear and you're putting like drops and it's not changing. And that's just that slow rise that's happening in pH. And your job was to get it from an acid to neutral, which is 7. And if you graph it, you'd see this slow gradual rise. And then you guys that have done that lab know that like just the flick of one drop could turn it dark pink. That's where the buffering has been overcome and it just shoots up. Okay. And then you start getting frustrated because you're like, it was just very light pink. I just added one more drop. Well, that one more drop took it past 7 and it made it dark pink, which is basic. Okay. And then you had to go back and back titrate it with more acid to fix it and then go from there. So that's you witness buffering as it's not changing color right away because that solution naturally has buffers built in it as you're adding that. Okay. We can make it even better. You guys were doing strong acid versus strong base. So there was less buffering. So it changed the graphs. You're going to see graph differences between the two. But when you're doing a strong base into a weak acid, it even hangs out even longer before it'll start to rise. And it resists that change in pH. Okay. By the way, if you need like real world examples of this besides the ocean, your blood is a buffered system. And the contents of your blood, it's basically carbonic acid in your blood. We'll look at that system. It keeps the pH of your blood between 7.35 and 7.45. And if it gets beyond those limits, you start getting health issues that are not good. So your body will naturally get rid of carbon dioxide faster if it needs to, or take in more to get the pH to drop. Because if you take in CO2 into the water that's in your blood, it's going to make carbonic acid, the pH drops. Okay. If you respirate and get rid of the CO2, it leaves your blood and the pH rises. But the buffer compounds in that blood will keep it about level. Okay. They even sell water designed to like pH, like I think it's horse feces. I can't say the SH word because I'm live streaming, but some of it's kind of, hokey. So I saw one that was like a pH of 9. And at some point it's going to start tasting funny. Like it's going to start tasting bitter. So I don't know. But so we end up, we're going to go through a problem here and show you guys how to work these. And then we're going to do one that involves all 3 of the steps. Some of them don't. But I think if you can get a couple of these, like where you see it, you can start to see the pattern and get through this. So the question says, this is a weak acid with a strong base being added to it. Okay. We don't do stuff with weak and weak because there really isn't going to be much of an effect. So AP focuses on weak with strong. Okay. The titration you guys did, if you took my class last year, was strong with strong, which gets the pH to 7. With these, the pH is going to be higher or lower than 7, depending on what we're starting with. If we start with a weak acid and we use a strong base, you'll see the pH is going to be it's going to be higher than 7 when it's neutralized. Okay. So we've got, the problem says, determine the pH when 45 milliliters of 0.5 molar HF, a weak acid, are combined with 25 milliliters of NaOH with a concentration of 0.10000 molar. The reason why the volumes have so many sig figs is they're using burette, which is the tube with a little valve on it that you guys that did this. Yeah. And you guys that haven't done one, you're going to do one this year in here. So like next week, hopefully we'll get one in. But the equipment itself goes to the 100th place. It's very accurate equipment. So that's why those are that way. Okay, so step 1 is do the dilution math. That means the move equation. Or if you like mechanism, she says the boom equation. But I do one for the acid and one for the base. So the molarity of the acid was given as 0.5 and its volume was 45. So then the question becomes, where the fudge is that 70 milliliters coming from? Yeah, you're adding those milliliters get added together. I'm literally taking, let's say it's not the burette and I'm just doing beaker stuff. I'm literally taking 45 milliliters of one and dumping it into 35 of the other. Is it 30? Sorry, 25. 45 into 25 of the other, the volume's going to go to 70. Okay. Sometimes they'll say things like volumes are additive on the AP test just to remind you that you should add them together. Okay. So I do it for the HF and then I do it for the sodium hydroxide. That's the weak acid. That's the strong base. And I end up, this is the concentrations right at mixing. Okay. We did this before in unit 7 when we were doing the precipitate ones. It's the same idea. You got to get the total volume. You can leave it in milliliters. It doesn't matter because they cancel out and you end up with the polarities. Okay. You can also convert them to liters if you're worried about it, but it's going to be the same answer. What I'm going to do, I'll leave the math there if you're still writing it down. I'm going to go on the other screen. I'm going to go to the next step just to show it here. So we have the stoichiometry part, and this will be something that we look at first here. The numbers, first of all, the table, we call it a BSA table because it's not technically an equilibrium thing that's happening at this point. We're just looking at the forward reaction of those two guys getting mixed together. Okay. And so you'll notice the before the HF is 0.3214. That's from the stuff we just did. Okay. So it's kind of like the initial almost when we're doing these calculations. So the 0.3214 is the before for that. The hydroxide is that. Remember, water, leave it out. And the F minus is 0 at the start. Okay. Now this is like that equation we looked at a few slides back where it was HA plus whatever makes this. So our conjugate base is showing here at 0 at the start. Okay. Now, this is why this is called the stoichiometry portion, and this is why I don't like doing dimensional analysis for this, because what I basically have is a limiting reactant problem. What's a limiting reactant? I mean, what is the definition of it?
How much you can make.
It will give you the max you can make. It's also the reactant that either runs out first or last. Which one is it? Runs out first. Okay, good. Okay. So if I look at those two amounts, they're in a 1-to-1 ratio. And on the AP test, these kinds of questions will always be 1 to 1 to 1 to 1. Okay. So rest that worry because they're not, if they do that to you, I'll buy you all, I can't be careful with that. They'll probably end up doing it this year. I've never seen it. Okay. So, and they usually keep it to what they say there. Okay. So which of the two is the smaller amount? Yeah, that means it's going to run out first. If they're in a 1-to-1 ratio, stoichiometrically speaking, we can make that comparison because it's 1 to 1. Okay. If it wasn't, we'd have to multiply by whatever the change is and then figure it out. But we're not going to mess with that. Okay, so that ends up running out completely, and I end up with that being that. So if that's running out completely, that's the change because it can't go any further than that because there won't be any left. Okay. And if they're 1 to 1, the change for that guy and the change for that guy should be the same thing. Okay. So that guy goes down to that. That guy goes to 0 because he got used up. This guy goes up to this because it started at 0. The water, we don't care. Okay. And it doesn't change. And the water's concentration can't change. It's water. There's nothing at it. It's the medium. Okay. So that's the initial of those guys going together. Then it starts going back and forth and they start trying to get to what condition? Equilibrium. And that's where the ice table comes in. So this is more complex stuff than you've done before. Okay. But I don't want to make it sound like it's impossible or you'll never figure it out. Okay. Cause it's doable. If I can figure it out, you guys can. Okay. Trust me. You guys saw me yesterday and the mistakes I was making, but I can figure it out. Okay. So again, it mentions here the initial values come from the after of the stoichiometry step. So those after values are where I start. Now we're in a regular equilibrium problem like we've normally been doing. Okay. It just took a little bit of work to get it to that spot. They're just adding in a few extra steps. Okay. So the initial for the HF is there. Now, here's what you're going to notice. What happened to the hydroxide? Why is it not in the ice table? It got used up. It's gone. Oh. Yeah. So you wouldn't have to deal with it anymore. Okay. And that's why we have to account for the hydroxide in that first table. We get rid of it, and then the system goes into an equilibrium thing. Okay. So now we go with, okay, this is our normal acid dissolving in the water thing we've been doing the last couple of days. Now we're back to what we've been usually doing, except instead of starting at 0, what's going on? Yeah, there's some in there because of this whole buffering mess that was going on before that. Okay. So again, it's what we're showing is because of the hydroxide being added to that solution, we're going to end up with a common ion that's showing up that's going to resist the pH change when this thing's all over. Okay. So now we look at, okay, that's our initial water again, don't care. But now we're looking at the H plus or hydronium, whatever you want to call it. The F ends up by itself. That's the conjugate base. The HF breaks up into that and that. If we just ignore the water, it's just that. But with the water in the equation, it's hydronium. Either way, how do I get the pH? I remember, what substance do I get pH from? The H. Yeah, the H plus. Okay.
So I have a question about that.
Yeah.
Do we always have to get one of one reactant?
Yeah, it's gonna do it.
Okay.
So when we get to titration, though, you're gonna see there is one spot where they both run out at the same time, and that's the equivalence point. No, don't. That's where it hits the light pink. If you're using the indicator,
So
when they're equal, you've hit the equivalence point, and there's a way to deal with that when we get there. So take it. It's a good question. Just take it in these small steps we're doing, because this is going to come back later in titration, this stuff. Okay. And this unit, no joke, you really can't zone out on this unit. Like it's tough because you want to zone out. Some people do. Some really want to know how to do this so they don't flunk. But try to resist that temptation. And I've been there. I missed a meeting Wednesday I was supposed to go to at 4:30 for Dr. Lutz because I'm his mentor. It was a mentor meeting, and it didn't send it to my Google Calendar when I registered for the meeting, and I didn't even know. I got a message going, I have to make up homework now because I wasn't there, and it sucks what I have to do. So I get it. I mean, I just zoned that day and I forgot all about it. So if you do something poorly enough, what will they do? Fire you. No, not from this job, from the mentor job. Exactly. I want to help Lutz because he's cool. So yeah. But I also don't want to do it. So it's like there's a battle there of not wanting to do it, but you need to do it. Okay. So these guys, that's what we're starting with. We don't know what's going to happen. So why the X's? We don't know. And why not take them into account? 5% rule. Okay. So all the problems we've been doing up to this point, guys, were just one of these, but everything was 0 except for the start. Okay. So like the warm up yesterday and the ones we did in the notes, it was just, there was something here. Those guys were 0. Now we're just saying, okay, there's something there. So we got to deal with it still. Okay. But whenever that happens in those common ion problems we did in unit 7, the math is easier. There's no square rooting because you've got something there. And at this point, I just got to figure out what X is. So how do I do that? Yeah, and it's our usual way of solving things. If that's the Ka, and they gave me the K value, I just have to plug my numbers in and I can get the H plus.
Okay.
Yeah. And then from there, how do I get the pH? Negative log, always negative log. And the pH of this stuff would be 2.28. So what we're doing today and Monday is it's really part of a bigger titration problem that could be given as a long FRQ. Strong acid, strong base titrations are so much easier to do the calculation. It's like ridiculously easier. But where it becomes AP is the weak acid, strong base, or weak base, strong acid titration. What's that? We don't mess with weak and weak because you won't see a significant change in pH with a weak with another weak. It'd be like a strong and a strong. It would just, yeah. I've never seen a weak and a weak problem. Yeah. I did not round that correctly. So then the next thing we deal with is the question we were talking about it earlier. What if they both run out at the same time? Like what if it's equally matched? Okay. And so let's look at this part. Okay. So this one says determine the pH when we have 100 milliliters of a solution containing 0.25 molar HF and 0.25 molar NaOH. And so step one, the dilution for this example is already done. So this would be an example where you don't have to do the M1V1. If they give you concentration and a total volume like they did, you don't have to mess with M1V1 equals M2V2. Yeah, it's already been diluted. Okay. Yeah. No, it says it right there. It's the same. Is it different? Did I? Oh, shoot. Oh, crap. Hang on a second. Okay, change it. Well, leave it at 6.6 times 10 to the negative 8. It's not the same. Yeah, let's just say we're at a different temperature. Okay. Yeah, I got to fix that. That's a mess. Somebody bought these notes too on Teachers Pay Teacher. Sorry, guys. Okay. I think it'd be easier to, well, which one would be easier to change? All the work is shown from each one, so.
I'll just get rid of that.
I'll just go back and figure it out.
We can just get rid of it because it's the same as that last.
I think this one would be easier to change. No, you have to know this for the AP test, so no, that's not happening. Okay, so just imagine it's the same, but it's 6.6 times 10 to the negative 8 for now, and then I'll go back and fix it for next year. Okay, so here's what we're saying. We're starting with equal molarities of both right at the start, and we're mixing them. And they've already been mixed, like it's right at that point that we've done the M1V1. Those guys are there. The F minus, again, starting at 0, the water, we don't care. Okay. There is... they're both going to run out, so it's not a limiting reactant thing because they're both gone. So if we end up with that, I have 0, 0, and 0.25 molar of the F minus, but this question is asking for what? Like, what's the question ultimately want? pH. They all want pH. That's like every question is, what's the pH? It's just situations are different. I can't get the pH from anything in that table. So I've got to go to step 3 and do the equilibrium portion. Okay. So once that F minus gets made, when I mix those guys together, whenever I have a weak acid involved, if that F minus gets made in the forward, what's going to start happening in the reverse? It's going to make some of these guys. Okay. So that's why I do the first initial, like it makes this. This is like looking at the forward reaction where it makes the stuff initially. Then the equilibrium table starts to, until they go at the same speed back and forth. Okay. And again, that's how I got my mind wrapped around these when I first had to learn them. I was looking at this stuff in college going, I have no idea what this guy's talking about. And I really had to dumb it down for myself to figure it out. Okay. And it made sense. And I think I even asked him, does it make sense that the stoichiometry part is the forward and the equilibrium is both forward and backwards? And he goes, yeah, that's your dumb monkey brain can figure that out if you do that. Okay. Both my chemistry teachers that I had the first couple of years barely spoke English too. That made it harder. Yeah. One was from Europe and one was from Asia. And I think it was harder to understand the European guy. I think he was German. Now you look at that and you're like, I should have dropped the class back in August. But no, I'm kidding. You shouldn't have. Okay. So
Bro, Marley was right. Bro,
Marley. Who was?
Marley.
Marley made the smart move. Except she won't get the 5 units of college credit.
Neither will we. If you don't,
If you don't pass.
Girl, please. I've gotten many a student to pass the AP test purely by dragging them through this with so many examples. They can only help but do it. You see it enough time. Okay, so let's look at what I wrote up there on the table. Notice the reaction is now reversed and it's an equilibrium system. I didn't put the double arrow, but it's yeah. So yeah, on this part, I flipped the equation. Okay, so you've got F minus water. We don't care. It's making HF and OH minus hydroxide. Okay. So remember, those guys were at 0 at the end of the last table. Now we're going to go into the equilibrium stuff. Okay. So now it looks like something you've done before, more or less. You've got a starting point. You've got zeros on these guys. We don't know the changes, so we use X's, and we ignore the change for the guy with the number because the K is really low on this one because I made it 10,000 times smaller. Yeah. So how do I get the pH from an OH? If I know the concentration of OH minus, I can find the POH and then subtract from 14. Okay. So when you guys are working, this is why the tables are really important to me, because as long as I can get to the bottom of each of those tables, I can make the move to the next table and then eventually make the move to doing a problem I've already done before. Okay. So what I look at here, I have a problem because the K has what label on it? Well, the K. It's an A. Okay. That's for an acid, but I'm dealing with a what? A base. So one of the equations that they give you on the AP test equation sheet is this one. And it helps you convert between, don't worry, we're going to be on this for a few days. Okay. It helps convert Ka and Kb from one to the other using Kw. Okay. And it's given to you. So if you get lost and you're like, okay, I got hydroxide's a base ion. I'm trying to get pH. This is ridiculous. I hate every professor that helped write the AP test and the teacher that didn't help me enough to get through it. And you're ready to throw it in. Don't, because just go to the equation sheet. That usually wakes me up when I get a problem and I'm not sure what they're asking. I go to the equation sheet and start seeing if something will, pop it loose in my brain. So to get the Kb from the Ka that they gave me, I just plug in the K-dub's given to you on the equation sheet. That's the 1 times 10 to the negative 14. Divide by that and I get the Kb. And then I just set it up like I normally do for a base. So this is why we showed both in topic 8.3. There's no other way to get this done. And it's a thinking person's problem. So yeah, it's not a give up and pray this doesn't happen on the AP test because they hit acids and bases on the AP test. Yeah. And yeah, if it's in, you're going to see some FRQs with this stuff in class to get you ready for how they. I mean, this is meant as like an FRQ type problem. Okay. Yeah, because when you're dealing with a problem like these and you go in reverse, you're going to end up with a base in there. It's because we added the hydroxide to this solution in the first place on the BSA table that this is happening. Okay. So when we look at this, because we're adding a strong base to a weak acid, who's got more power in this? The strong base. Yeah. And it's if it's sodium hydroxide, which it is, how much of that sodium hydroxide, really, this is an important question. How much of that sodium hydroxide breaks up into ions if it's strong? Almost all of it. Yeah. So there is a lot of hydroxide in that solution. It got used up initially, but now it's going to start coming back out again. Okay. And that's going to really drive the pH when we look at that. So on that last part, you're seeing, oh wait, sorry, actually I went forward on this. Yeah, what you're actually seeing is the effect of all that OH that's in there at equilibrium, because the OH concentration, it's not like huge, but it's affecting the pH. Okay. So when I calculate the POH, it's 3.71. If I negative log that, I get 3.71. To get the pH, it's always 14 minus. 14 minus that is 10.29. This is a weak acid with a strong base, and the pH is what?
High.
Yeah, it's basic, like my sweat. My what? My what? Oh, my ex? Oh, yeah. Yeah, she was. Yeah. She's from Texas. Okay. She really was. All my exes live in Texas. She's from Houston. No, my wife's from the Bay Area. Yeah. She's from the East Bay. Yeah. Sure she is. Yeah. So, yeah, when we end up in this situation, yeah, why we're doing this now is when we get to titration, you're gonna see this again, and you're gonna be like, oh, we did that already. Okay. So what's happening here always occurs at the equivalence point in a titration where we're mixing acids and bases. When the concentration of the acid equals the concentration of the base, like we just saw, because it was 0.250 and 0.250, that is known as the equivalence point. That's what we're looking for in a titration. For a strong acid, strong base, what's the equivalence point pH? Always. 7. Yeah. If it's a strong base with a weak acid, the pH of the equivalence point is higher because the base is broken up completely into ions. The acid is not. What if we reversed it and had a strong acid with a weak base? What's the pH going to be when they're at the equivalence point? Lower than 7. Yeah. So you could actually do analysis of chemicals and figure out if it's a strong acid or a weak acid or a strong base or a weak base just by looking at the pH when you're done mixing them together. Okay. You'd have to know the molarities of each, but I mean, this is what we end up doing in these types of labs. So then it becomes, you got to find an indicator that changes color at that point, or use pH meters, which you guys are going to hopefully be using in the lab we're going to do for this. Okay. So yeah, this is fun stuff. This is the opposite of fun. Okay. Yeah, this is really not. It is for me because I've been doing it and I like the challenge of it. But the stakes aren't as high for me. Yeah. Because it's not my grade in the balance or my job. Even if you guys scored low on the AP test, it's happened before. They still have me teaching AP Chem. Why? So 1 year of that. So is that why you fired? Okay.
What if it's
I'm
like
fine
3
with it.
years of,
It's less stress if I don't have to teach AP Chem.
what if it's like 3 years of bad scores?
We had 3 years of bad scores during COVID.
Oh, well,
That was a nightmare. Yeah. Trying to teach this class on Zoom. Try it. Okay. Let's look at the opposite. Let's look at a weak base. I know. I wish Henry was here right now. Okay. Look how nice I was. I already did the dilution part, so you don't have to worry about that right now. Okay, let's focus on just yeah. Okay. This stuff's so hard, I might take my sweatshirt off. Oh, I know. Getting hot. Is it hot in here? Okay. So, NH2OH. What's the name of that stuff? I already forgot. Let me see. This is embarrassing. Oh, hydroxylamine. I should have known that. Colorless, hygroscopic, unstable inorganic compound used primarily as a reducing agent in photographic developers. In the old days, they used to have film and a camera, and this chemical was one of the things that helped develop the negatives. Yeah. When I took film in high school, that's what we did. Okay. So step one's already done. And they gave us a KB in this case, which means you're probably going to have to change it to KA later. Okay. So when you look at the amounts there, okay, what's the limiting reactant in this problem? H plus is running out this time. Okay. So the changes are given there. And then it says at the bottom, note that the weak base Na2OH and the NH3OH plus are pretty much equal. Okay. This is, you're going to see this in the titration topic later. This is known as the half equivalence point. What we saw earlier was the equivalence point. This is known as the half equivalence point. And bear with me, this is going to give you a way to solve these problems that's a lot easier. Okay. When we get to it. Okay. So it says we were given a Ka, but now we're working with a conjugate base. So when you guys look at that equation, notice we have the base with water, and it's making the conjugate acid, which is NH3OH plus. Okay. And hydroxide, which is a base. Okay. So Kb is 9.1 times 10 to the negative 9. And if you solve for x, what's true about the Kb and the x? Yeah, it's the same. And this is known as the half equivalence point. Okay. And a titration. Again, if you're just get down the idea of what these are now, we're going to really get into like doing these. Okay. So if you negative log that OH that's there, you solve for x, you negative log it, you get 8.04. Okay. But the question's asking for what? pH. So, and this is a mistake I routinely make, where I forget to do the conversion to the pH at that point. And so always be mindful of the ion that's involved in the table. In this case, it's hydroxide. And then always be mindful, they're usually going to ask for the pH on these questions, because that's what most people understand is pH scale. Okay. There's actually a meme for this. Do you want to see it? Okay. I'll put this back. I'm just going to show you this. Most questions are pH related, not. He gets one little tiny microphone. All the attention is given to pH on the AP test, not the POH. Okay. So when they give you OH, go, that is a trick. That is a scam. I got to work my way back to pH and do 14 minus. Okay. So this is a strong acid weak base problem. And notice the pH on this one is 5.96. It's acidic, but they're equal. Or at this point, they're not equal. But at this point, yeah, the pH equals the pKa. Or you can say the POH equals the pKb. So the pKa is the negative log of the Ka, and the pKb is the negative log of the Kb. Anytime you see little p, what do we have to do? Negative log. Yeah, that's all it means. Okay. Nobody actually knows what the little p stands for. When Soren Sorensen was making the pH scale, he never fully explained why he used a lowercase p. We think power, like exponent power. Yeah, but there is no actual. So I just think it means negative log. When I see lowercase p in chemistry, I think negative log. Okay. So yeah, this is really important. The half equivalence point is a really easy calculation. If somebody, if a question asks, hey, what's the pH at the half equivalence point? You don't have to do all of this, is what I'm ultimately getting to. And you're going to be like, well, why'd you show us this? Well, you got to know what it looks like. Like at this point, those guys are equal. That means they're going to cancel out in the math. And if that is equal to the conjugate acid, that means that the pKa equals the pH at that point. So when you get a question where they're like, hey, what's the pH at the half equivalence point? Just find the Ka and negative log it, and you've got your answer. Okay. And that you'll see enough examples where you'll know to do that by the time you get to a unit test. The people that are locked in will know to do it when they get there. Okay. And they usually get that question right on the test in here because it's like that's an easy one. You hope it's that and not the equivalence point, because the equivalence point you got to do what we did earlier, which is all the stuff. Half equivalence point, titrate, or pH calculations are the best. Okay. For that. Okay, so do I have to do step 1 in this problem? No. It's all right. You already got them. Yeah. So first step then is to do a BSA table. Okay. Before shift, or yeah, however you want to put it, but it's basically like an ice table, but for the forward reaction. So before you guys do that, what is the equation for this thing? Yeah, and let's make it even simpler and get rid of the the stuff that's not part of the equation. Like let's do the net ionic. Let me just bring up my we'll start this one and then finish it on yeah, so we have HA plus OH minus, and what's going to be on the other side? A. That's our conjugate base. H. Double replacement. Who's going to end up with the OH? Yeah, so you've got, this is H plus, A minus, this is OH minus. That gets together with that to make H2O. So we have our equation there. Okay. What's going to be left out of the ice table or the BSA table? H2O, because it's a liquid. Always leave it out. And then you've got your stuff. So what's our start for the HA? 0.38. This is 0.12. This is how much? 0. That we don't care about. What's going to run out first? That'll go to 0. That'll go to 0.26. What's the A minus going to be? Plus 0.12. So now we've got our first part done. Okay. And so we get to that. Let me just show you the typed one just so everybody can see it. So we end up with that stuff going on when we get to that part. Then we do the ice table. So for the ice table, the HA is now going to be mixing with the water. Okay, so the HA mixes with the water. And this is where we see this, just to show you guys. Okay. So the first step is mixing that strong base with the weak acid. That's the buffer problem. And then the second part is, okay, let's look at the weak acid dissolving in the water. And now it's got a common ion because of what happened with the buffer. Okay. By the way, to really make this more confusing, all of this is happening at the same time. We're just doing it in steps so we can make sense of it. Yeah. You did good. Don't worry. It'll get better. Okay. It will. I promise you. I am making it.